Welcome everyone, I'm Brian Walsh, and in today's lesson, we're going to look at the relationship between the ideal gas law and reaction stoichiometry. So in previous lessons, we learned about general stoichiometry, we learned about solution stoichiometry, and now we're going to look at how to incorporate the ideal gas law when we're dealing with stoichiometry problems.
Let's take a look at the relationship between the ideal gas law and reaction stoichiometry. So our ideal gas law is PV equals nRT, and this is our diagram for our reaction stoichiometry. So our reaction stoichiometry diagram here is sort of a roadmap for conversion. It tells us how to convert between units within the same substance, and it also tells us how to convert from one substance to a different substance using the balanced equation. So you might be wondering, what does this have to do with our ideal gas law? But if we look a little bit closer at our ideal gas law, what we have is pressure times volume equals moles of gas times the gas constant times temperature. So included within our ideal gas law, we have this N moles of gas, which means that we can use this equation to find moles of gas. And if we know moles of gas, that puts us right here on our reaction stoichiometry diagram. And from here, we can convert to atoms or molecules, liters, or grams within the same substance. Or if we know the balanced equation, we can convert from moles of this substance to moles of a different substance, and then from there to each one of these things. Which means that as it is, our reaction stoichiometry diagram is not quite complete. We need to add something that includes PV equals nRT. So we add these two segments to our diagram. And what this shows us is that if we know the pressure, the volume, and the temperature of a gas, we can use PV equals nRT to find moles of that gas. And once we know the moles of that gas, we can convert anywhere else on our map here. So let's go ahead and take a look at a sample problem to see how this works. So this problem asks, what volume of H2 gas at 765 torr and 225 degrees Celsius is needed to react with 35.5 grams of copper 2 oxide? And they've given us this balanced equation. So they've given us 35.5 grams of copper 2 oxide, and they want us to convert those 35.5 grams into volume of H2. So we're converting grams of copper 2 oxide to volume of H2. So looking at our stoichiometry diagram, we've been given grams of copper 2 oxide, and we've been asked to find volume of H2. So we're going to go from here to here. So we can see that the first thing we need to do is to convert grams of copper 2 oxide to moles of copper 2 oxide, and we do that by using the molar mass of copper 2 oxide. So we start our calculation with our 35.5 grams of copper 2 oxide, and we're going to convert from grams of copper 2 oxide to moles of copper 2 oxide using the molar mass. And using our periodic table, we calculate the molar mass of copper 2 oxide at 79.55 grams per mole. And this is rounded to 4 significant figures. So we set up our conversion factor so we have grams of copper 2 oxide on bottom to cancel with our grams on top here. So these grams cancel with these grams, and now we have moles of copper 2 oxide. So now we're here on our diagram, which means that our next step is to convert our moles of copper 2 oxide to moles of H2 gas, and we do that by using our balanced equation. So looking at the balanced equation, we see that we have 1 mole of copper 2 oxide per 1 mole of H2 gas. So we set up our conversion factor so that we have moles of copper 2 oxide on the bottom to cancel with moles of copper 2 oxide on top. So these cancel with these, and now we're left with moles of H2. So now we have moles of H2, which means that we're right here on our diagram, which means that we have only one more step, which is to go from moles of H2 to volume of H2. And we're going to do that by using our ideal gas law. And since we're going to be using a different equation on our last step, we can go ahead and do our calculation here and solve for moles of H2. So we multiply 35.5 times 1, and then divide by 79.55. What we get is 0.446 moles of H2. So now we're going to use these moles of H2 to convert to volume of H2, and we're going to do it by using our ideal gas law. So we're going to be using this equation to solve for volume. In the problem, they told us that the pressure is 765 torr. We know that we're trying to solve for volume, We just calculated how many moles of gas we have, which is our N value. R is the universal gas constant. Finally, T is the temperature, which they gave us in the problem as 225 degrees Celsius. We can see that V is our only unknown, but before we can plug these values into here, we need to make sure that everything is in the right unit, which means that we need to convert torr to atmosphere, and we need to convert Celsius to Kelvin. So we can start by converting torr to atmosphere. So we start our calculation with our 765 torr. And if we remember our conversion factors, we can see that we have 760 torr per 1 atmosphere. So we set up our conversion factor so that we have torr on bottom to cancel with torr on top. So these units cancel with these units, and we're left with atmosphere. So we multiply 765 by 1 and then divide by 760. And what we get is 1.01 atmosphere, which means that our 765 torr is equal to 1.01 atmosphere. Now we need to convert our Celsius to Kelvin, and we do that by adding 273. So we do 225 plus 273, and we get 498 Kelvin. So now that we have everything in the right units, we can go ahead and plug these values into our equation. So our P equals 1.01 atmosphere, so that goes here. V is what we're trying to solve for, so V stays V. Our N is 0.446 moles. R is our gas constant, and T is 498 Kelvin. In order to solve for V, we need to get it by itself on this side of the equation, so we're going to divide both sides by 1.01 atmospheres. Now, looking at the left side of the equation, we can see that we have 1.01 atmospheres over 1.01 atmospheres, which means that those cancel, leaving us with just V on the left side of our equation. And if we look at the right side of the equation, we see that there's lots of units that we can cancel also. We have moles on top here and moles on bottom here, so these cancel. We have Kelvin on top here and Kelvin on bottom here, so those are going to cancel too. And finally, we have atmospheres on top and atmospheres on bottom, so these atmosphere cancel with these atmosphere, which means that when we do our calculation, the unit that we're going to be left with will be liters. So we multiply 0.446 times 0.0821 times 498, and then divide by 1.01. And what we get is a volume of 18.1 liters, which means that our volume of H2 gas is equal to 18.1 liters.
If you have any questions about anything, or if you have any feedback that you'd like to give me, please leave me a message. You can leave a comment, or you can email me at chemistrymadeeasy118@gmail.com. Thanks for watching.